I'm Gerd Zellweger. I'm going to tell you about decoupling cores, kernels, and operating systems. This is joint work we've been doing at ETH Zürich together with my colleagues Simon Gerber, Kornilios, Kourtis, and Timothy Roscoe. So to give you a short outline about the talk, I'm going to factor this into three pieces. First, we're going to see motivation that led to this work based on trends in hardware and software. And then we're going to see how we built an infrastructure for booting and shutting down cores dynamically. We used there a way to decouple the kernel state, and this has some interesting use cases that we're going to see in the last part in the evaluation section, for example, to do kernel updates or running specialized kernels in our OS. So, what is happening to hardware? Well, today we're mostly constrained by power consumption. This has brought us, for example, reconfigurable cores, meaning we can dynamically change the behavior of our cores. So this is already true today with voltage and frequency scaling techniques, turbo boost or SMT. On the other hand, there are research techniques such as core fusion, which allow us to fuse cores, multiple physical cores into a single more powerful core or split them up again. On the other hand, in the future, we may have to deal with dark silicon, meaning we can have many cores, but we will not be able to power them all at the same time. So what does this mean for us for adding and removing cores in the system? Well, we already do it today, for example, if a core fails or if we allocate cores to different VMs in our machines. On the other hand, if we fuse core, we dynamically rearrange the core count in our system, or we have to maybe take cores out of service because we will not be able to power them all at the same time. Also, we have heterogeneous cores in our machines, giving us asymmetric performance. And for example, one such logical conclusion of this would be conservation cores, where they build very workload-specific cores, and as the workload changes in the system, they switch between those cores. Now imagine having to build an OS in a dark silicon era. So you have a set of heterogeneous cores, and you need to switch between the cores based on your workload, but you also need to power down and take cores out of service because you don't have the power to power everything at the same time. So how would that look like? Well, today we mostly have a contemporary model today is that we have a kernel running as a single program on all the cores. Every cores run the same code, and it is hard to adapt to, for example, heterogeneous cores. So what happens if we remove a core in such a system? Well, we have to go and update a lot of internal data structure to reflect this change. Typically, this requires global coordination, and also, the data structures may be globally shared, protected by locks. What happens if the processor is holding any locks? So there are a lot of issues there. So the same is true if we fuse a core. We typically have to deal with the per core state. You have to go and merge, for example, per core scheduling queues and so on. So at the same time, in software, we usually need to adapt to different workloads in our OS. Now, general purpose kernels are helpful for that, but we still have to adapt or modify at build, boot, and runtime, for example, to facilitate debugging support with profiling or tracing. And sometimes the application requirements are very strict, such as with real-time support, and it is hard to fit everything into a general purpose OS kernel. Now, there are also research techniques that work by modifying or upgrading kernels on the fly, as is the case, for example, with ksplice in Linux or K42 update mechanisms. So we argue that a good architectural model for dealing with dynamic cores or adapting to heterogeneous cores or changing software requirements is a multi-kernel model. In a multi-kernel, each core runs a separate kernel program, and state is carefully factored into per core state into what we call an OS node. Now, we still have to run applications on top of that, and applications may share state between cores. Therefore, we replicate state between cores using asynchronous message passing. So, however, the multi-kernel model alone is not enough for dealing with dynamic cores. So what happens if a core goes away here? We still have to deal with the OS node and all the running applications inside it. So therefore, we use as a basis for our work the Barrelfish OS, which is an implementation of the multi-kernel, and we add some features to Barrelfish that treats cores as much as possible as pluggable devices. So we'll see in the next part how we boot a core dynamically with boot drivers and how we shut down cores in our system. We use there a technique that externalizes the kernel state, and that allows us to decouple cores, kernels, and the operating system. So how do we boot the core in Barrelfish? Well, typically this is not a hard problem. The key things to note for this talk here is that we do have an OS service that can do target core management, and we can dynamically choose the kernel for a core based on runtime information. This allows us to boot any core with any suitable kernel, and we can run any OS node on any compatible core. Aside from booting, we also implement shutdown or reboot protocols. So how are we able to shut down a core in Barrelfish? Well, typically, as I explained, this is harder than booting a core because we now have to deal with per core state. So what happens to scheduler queues? We need to merge memory pools and free page tables and so on. This takes a lot of time and energy. However, in our case, we want to shut down a core as fast as possible. Why do we want to do that? Well, first of all, we want to use it as an energy-saving mechanism, and some of the use cases we will see later require that we are able to shut down a core fast. So the general approach we follow here is inspired by Chameleon, where we get state out of the way quickly and dismantle it lazily later if we need. So how does that work in our OS? So if a core goes away, we are able to capture this OS node or all the per core state, and we move it to a different core. Now we added an OS node scheduler in the kernel that is able to dispatch different OS nodes. We call this case where we have one OS node and we move it to a core that already has an OS node, temporarily parking an OS node. Now we can already note here that this approach is highly scalable as we only involve 2 cores in the process right now. We don't need to globally coordinate it in the system. So what happens next? We can either dismantle the state of the OS node, or we can move it back, or we can move it somewhere else. So what is this OS node and how are we able to capture it all? This is typically not clear in any OS. Per core state is usually not explicitly defined and typically lives in many different data structures. So we use a partitioned capability system to explicitly capture the OS node, meaning the entire per core state, in a single data structure. This captures all access information and memory allocations of applications. So all per core state in the kernel can now be accessed through this structure or reconstructed from the capability tree. We still need to be able to reach this structure and pass it around in our system. Therefore, we added a KCB, or kernel control block. Now, the KCB contains some state that currently does not fit in our capability system, which is mostly hardware-specific state, such as interrupt vectors. And it also has the entry points to access the capability tree. Now, the KCB is a capability itself, meaning we now have a representable handle in our system to move entire per core state around. So, this method of state externalization and dynamic core booting is a much more general mechanism because we are now able to move per core state around arbitrarily in our system, and we can also replace kernels dynamically underneath OS nodes. As a part of the relation section, we're going to see how exactly we do this and how fast it is. So in the relation section, I'm going to focus on 3 parts. First, we're going to see core management capabilities, or how fast can we add and remove cores in our system. And then we're going to see a use case where we dynamically replace a kernel underneath an OS node by hot swapping the kernel binary. And in the last part, we're going to see one use case where we run specialized kernel in our system to eliminate OS jitter. So, to talk about core management first, we have here a Haswell machine with 4 cores and hyperthreading disabled, and we're going to look at how fast we can boot a core in our system. We distinguish between 2 cases, one where we don't have load in the system, and one where we generate load in the system by stressing the OS with system calls. So to give you a comparison, we compare this with the Linux hot plug facilities. And in Linux, it takes about 14 milliseconds to boot a new core. And if we have load in the system, this increases slightly to about 20 milliseconds. So if we do the same thing in Barrelfish, it takes about 7.5 milliseconds. If we have load, we are not impacted by load, it takes about the same time. So now don't read too much into these numbers. The Linux kernel and the Barrelfish kernel are obviously very different. Linux typically has to do more initialization work, whereas in Barrelfish we actually have to load a kernel from a RAM file system first. However, if we remove a core in our system, we do the same thing. We look at the numbers for Linux first, and we see it takes about 46 milliseconds if we don't have load. However, if we add load in the system, this time goes up to about 2.5 seconds. Now here we really see the impact of having to do global coordination and dealing with the per core state in Linux. In our case, it takes about 0.8 microseconds to remove a core in the system. Now, Chameleon addresses this problem in Linux, and we would expect their numbers be comparable to us. However, we also have to say here that we don't dismantle actually the per core state, but we remove it. We move it around just lazily in the system. However, in many cases, we do not actually have to dismantle the state, as we'll see next in some of our use cases. So how would we update a kernel in our system? Well, we can just shut down the target core, and then we essentially reboot the core with the new kernel and passing it the previous OS node. From an application's perspective, this will just look like as the application has not been scheduled for a while. So to evaluate the use case, we have here running PostgreSQL with the TPCH database inside our OS node, and we measure latency of queries on the y-axis with queries over time on the x-axis. Now at some point we hot swap the kernel, and we see that this produces some outliers because we actually need to reboot the core. So the outliers are about 10 to 15 milliseconds, and notice that this is the same Haswell architecture where it takes about 7.5 milliseconds to boot the core in the system. So another use case would be, for example, temporarily run a real-time task in our system. Typically, we have to do this if, for example, we need to have a phone baseband stack, or we have some controlling applications in robotics. And in general, a lot of time and effort is spent to make this work in a general purpose OS. And still, many people rely on real-time operating system to do these things. So how would we do this in our system? Well, if we have a machine with 2 sockets that runs our OS, we could simply swap one of the kernels with the specialized kernel, real-time kernel here. And if we want to have, for example, cache isolation, we could get rid of the entire socket by temporarily moving the OS nodes around in the system. So to evaluate this use case, we're going to first move the OS node and temporarily park it on another core. And so we can now free up space on the core. So we see here this parking where we again have our PostgreSQL instance with a TPCH database inside an OS node. And in the first part, we have 1 OS node per core, and we see that query response time is about 40 milliseconds. At some point, we temporarily park the OS node, and currently we strictly time shares OS nodes between on the core. Therefore, the latency increases up to about 80 milliseconds. Afterwards, we're moving the OS node back to its original core, and the query response time normalizes again. So now that we have freed up one of the cores, we can boot this with the special kernel, and we build a simple real-time kernel that essentially does not take any interrupts. It doesn't have any timer in the kernel, or it doesn't have a scheduler. It's designed to just run a single application. So this kernel will construct its own OS node and temporarily run our real-time task. Now, to evaluate this use case, we build a simple benchmark program that essentially does memory stores in the system. So we first run this program on our normal Barrelfish kernel, And the benchmark works by doing about 1,000 memory stores, and we repeat this experiment 1,000,000 times. So typically, each of these 1,000 memory stores takes between 6,000 and 7,000 cycles. But however, in our Barrelfish OS, we have some samples that are outside of the 6 to 7 cycle range, which we attribute to OS jitter. So if we run the same in Linux as a real-time task, we see that we do better in general, but we still produce some OS jitter because typically it is hard to get rid of all the jitter inside OS. Now, if we do the same on our Barrelfish specialized kernel, we see that all the samples fall into the 6 to 7K range. Therefore, we can successfully eliminate OS jitter in the system. So, to come to the future work and applications that we would like to explore, well, this concept of having an OS node, which is an entire per-core state, works great if we want to move between, for example, power-efficient and high-performance cores. On the other hand, as kernel developers, we're interested in dynamic OS instrumentation, for example, for profiling and tracing kernels, which we can simply do now by swapping kernels with debug kernel. Also, to test the impact some of our features have in the kernel, we can simply swap kernels to do A/B kernel testing, for example. Or we have seen the Arrakis talk before, which is essentially a specialized kernel that runs applications in guest string 0. And with our method, we can simply run this Arrakis OS on some of the cores and move it back later. So to conclude here, we started out with starting and stopping cores in the OS. The result is a highly dynamic OS architecture where kernels can be rebooted, updated, and specialized, and cores can be allocated and deallocated arbitrarily. So for many versions of the dark silicon hardware, this may be the only way for system software. So we'll make this code for this work available. It will be coming in a future release of Barrelfish, which will happen in the next 2 or 3 weeks. Thank you.
Hello, Chris Frost at Google. Enjoyed the talk. Question, in the previous talk we heard some about hardware interrupts, say, being programmed to be routed to a specific core. When you turn off a core, were there features like that being used, or do you have a feel for how that would impact the amount of time required to turn off a core?
Yes, so I can talk about interrupts specifically if you're interested. So I have some slides there. So maybe in general, we distinguish between 3 types of interrupts in our system. First, we have some interrupts that are handled locally to the kernel, which are, for example, timers in the kernel itself. Then we have interprocessor interrupts, IPIs, which we send between OS nodes. And here we use an indirection table that maps OS nodes to physical cores. And then we have device interrupts, right, which are essentially, for example, device drivers. In our system, they run in user space, and we need to reroute them to the new core. So what happens if we have a device that runs on some core and we migrate it to a different core, like now we essentially mask all the interrupts on the core, and then we have to re-register the interrupts on the new device driver. So typically, during this process, there is some time that's happening in between, and we have to go and check again if something happens in the device, or you can pull the device, right, while you're doing this shift. Okay?
Thank you.
Thanks.
Hi, I'm Srivatsa. I'm from MIT. I had a couple of questions regarding the power management features that you talked about as one of the main motivations for this talk. So given that you get power savings in a CPU going to CPU idle states, is it really necessary that you actually shut down the code to get the power savings? For example, in the Linux kernel, the model which people are following is to enhance the scheduler to have power management features so that it knows which of the cores are power efficient and manage coupled CPU idle states and so on. So what are your thoughts on this?
Right, very good question. Yes, you're right in general, right? So I think this work goes a bit a different way, where we say, okay, we want to completely get rid of the core, right? We don't want to keep the core running, or don't have, like, for example, to wake it up occasionally, right? So we want to explore a different direction here that is usually taken, I guess. So, yeah.
Thank you.
Henry from Stanford University. Question about the cost of actually disassembling your state after you park. So as you mentioned, your parking is very fast, but if you actually wanted to get rid of it, how long does it actually take?
Yes, good question. So the answer is it depends. So in typical, what we do, what the model we follow is that we upcall to the application once we dismantle the OS node. And the application, or the runtime system in that case, should have the knowledge to dismantle its state on its own. So what do we have to dismantle in our case, which is mostly, for example, messaging channels, which are shared between two parties. So you can dismantle that by communicating between the two. And then there is memory regions, which we have to dismantle by communicating on finding consensus in the OS nodes that share the regions in general.
Do you have any idea of how much time this actually takes on average or median?
It depends. It really depends on the use case, right? It depends specifically on how much you share between OS nodes, and how much state is shared between the applications themselves. So no, I cannot give you any numbers on that.
Thank you.
Okay, thanks.
Hello, Malte Schwarzkopf from Cambridge. I apologize if this is in the paper. I've only just skimmed the future work section, but you say in there that you assume cache coherency right now, because you obviously have to copy the OS node state from the memory that's associated with the core you're shutting down. Now, if you were moving to a non-cache coherent world, then presumably you would require a more expensive sort of teardown routine on the core that you're shutting down, right? Because if you assume a sort of failure model where it just blows up, then there's no way you can get the state. Do you have any ideas of how you could improve that situation, how you could make it faster, whether you could use the boot up if you're swapping the kernels on that code, whether you could use the boot up of the next kernel to help you swap the state or something like that?
Right. No, I don't have any. I don't have any clear idea how this would work, mostly because we didn't really use it, or we didn't really build a system like that so far. So, in typical, yes, you can transfer, right? So the OS node contains all the information that you need to copy, but you're gonna have to copy a lot of state in that case. But yeah.
All right, thank you.
Great, thank you.